In this video, we're going to look at sequential graph matching. Matching in a graph is the pairing of neighboring vertices. And it has lots of applications, such as pairing people in online dating services, but also pairing donors with recipients for organ transplantations in medicine, but also in scientific computing, for example, pairing rows and columns to get a good pivot in matrix computations. So first we define some graph terminology. So a graph is a set of vertices V and a set of edges E. And the vertices, they're also called nodes. The edges, they are the connections between them. And then an edge is a pair, E equals UV, with U and V and V. And we assume that our graph is undirected, so we identify UV with VU. They are the same. We also, in this case, assume that every edge has weight. You can think of it as the attraction between two people, but it can also be something else. And furthermore, we use the common notation of n for the number of vertices and m for the number of edges. This is an example of a matching in a graph. We have 8 vertices, we have 12 edges, and the matching is defined as a subset of the edges. So the thick edges, they are the subset M. And for a matching, you cannot have that 2 edges are incident on the same vertex V, that they share a vertex. So if UV and U prime V are both in M, it must be that U and U prime are the same, so that there is only a single edge. Here we have given weights to the edges. The cardinality of a matching is just the number of edges in the matching. In this case, that's 4. The weight of a matching is the total weight of all the edges in M. So in this case, the total weight is 42, because we have edges with weight 9, 10, 11, and 12. And the edge-weighted maximum matching problem is then, find such an M that the maximum weight is omega of M. In this case, is the answer 42. And if the answer is 42, you don't need an explanation. But if you want a proof, it's very simple. With 8 vertices, we can have at most 4 pairs. We do have 4 pairs here. And the pairs, they are the heaviest ones among the 12 edges. So this is indeed, 42 is indeed the answer to the maximum matching problem. So now a question to you. I have a line graph here with weights 1, 2, 3, etc. up to 9. What is the weight of the maximum matching for this graph? Well, the answer is 25. In this case, we conclude that if we have all the odd weighted edges, 1, 3, 5, 7, and 9 in the matching, then we have the maximum. And it's easy to see that you cannot have more than 5, or in this case 1, 3, 5, 7, 9. You cannot have more than 5 edges in the matching, and if you have 9 in the matching, it excludes 8. So this is a simple argument, and then you get to 25. Okay, so what is the fastest algorithm to compute a maximum weight matching? It can be done in polynomial time, as Gabor proved in 1990. The order is then m times n plus n squared log n. Now these are big numbers if your graph is big. For example, if we want to match all people in the world, let's say that's 10 billion vertices, and each has 1,000 friends among which you choose your match, then we have n equals 10 to the power 10, and m equals 10 to the power 13, and this order turns out to be 10 to the power 23. Now I express the number of operations then in petaflops. A petaflop is 10 to the power 15 floating point operations, and then we still have 100 million petaflops. If we take Fugaku, which is the fastest supercomputer in June 2022 for a high-performance conjugate gradient algorithm, which is a sparse matrix computation, and graph and sparse matrix computations run at this speed, then the speed of that computer is 16 petaflop per second. And then you can do a simple back-of-the-envelope computation, and you see that you need 72 days to solve this big problem. The one-world matching problem, I call it. That's a lot. You probably don't want to spend more than 2 months on a supercomputer, a top supercomputer, to solve this problem. So what we need is something that is not cubic, like this algorithm, but even less. Linear time would be best. And then you need greedy algorithms or approximation algorithms. So what's an approximation algorithm? It's an algorithm that solves a problem within a reasonable time, but with a guarantee of how far it is from optimality. For example, for the weighted matching problem, that omega n will be guaranteed to be alpha times the optimal solution, omega of m star. M star then denotes a maximum matching. Here we have a dominant edge, and a dominant edge is defined as an edge with a weight higher than all the edges that are incident to its endpoints. So here you see omega v, omega of uv is larger than omega e for all the e's that you see in this picture. And that's true because 10 is larger than 731, larger than 2 and 4. Larger than or equal, that's sufficient. That's a dominant edge. This, if we choose the dominant edge, this 10, we cannot include anything else. This actually would not give the maximum matching, because if you include 7 and 4, you get a weight of 11, which is higher, and that is the optimal matching in this case. Here's the basic dominant edge algorithm, which was proposed by Robert Price in 1999. And it works as follows. You start with an empty matching, and you continue until you have depleted the whole edge set. What do? You pick a dominant edge, uv, in the current edge set, and then if it is dominant, you add it to the matching. And then you remove all the incident edges. So anything that is incident to u or to v is removed from the edge set E. And also you remove the vertices u and v from v. And this you can do until there's no edge left. There can still be unmatched vertices left. This is the basic dominant edge algorithm. Okay, let's prove the half approximation property. And for this, we define first M is the matching produced by the algorithm. And M star is the matching with maximum weight. So it's the optimal one, but it is unknown. Still, we can use it in our proof. And we write it as a set of edges E0 until Ek with a star. And then we define corresponding edges corresponding to those in the optimal matching. We define corresponding edges EI in M by EI. If such an edge EI star is in M already, then we don't need to take something else. If EI star is already in M. And otherwise, it will be the edge that removes EI star from the matching in the algorithm. And clearly we have that the weight of EI is then larger than or equal to the weight of EI star. Because if they are equal, then of course we have equality. And if, in this case, EI star has been removed, it's a dominant edge algorithm, so it's been removed by an edge that has a higher weight or equal weight. So this holds. And then we can write the weight of our optimal matching, omega of M star. It's by definition the sum, because these are the edges in that matching, I equals 0 to k minus 1, omega EI star. And by that property, this is less than or equal to the sum of I equals 0 to k minus 1 omega of EI. These are the matches from M. Now I want to again have another inequality, but for that we need to look at a picture. Let's say I have a vertex here. And a vertex here. Okay, so this is EI star, and it has been removed by a dominant edge EI. This one is dominant. Let's give it a different color. Very dominant. But at the same time, it has also removed EJ star, because this one removed both. So you can see that a single edge can remove during the algorithm two edges from the optimal matching, but not more. Why not? Well, in the optimal matching, I can only have one edge on this side, because we cannot have two edges in a matching that share this single vertex. And the same here. So we can have one on this side, one on that side, and that's it. Now, we can continue with this realization. We can continue here, because here I get, this is a subset of all the EIs in the matching, of all the edges that are in the matching. And it can even be that this subset has duplicates, but not more than one duplicate for each edge. So I get a subset which is at most twice the whole set M produced by the algorithm. So this is less than 2 times omega of M. And here we have it. Thus, omega M is larger than or equal to half the omega of this unknown but optimal matching. If we implement this algorithm, we could do that by having mutual preferences or non-mutual preferences. Every vertex sets a preference to its highest weighted neighbor, the one it's most attracted to. And then if this happens to be mutual, we have a dominant edge. So properties of the dominant edge algorithm are that you can go on as long as there is an edge, there is a dominant edge, because just take the one with the largest weight of everything that's still there. It must be dominant. Also, dominance is something you can check locally, and that means that it is easily parallelizable, because you don't have to look far. You just need information on your neighbors, and then you already can decide whether a certain edge is dominant. Okay, let's summarize what we've learned here. A graph consists of a set of vertices V and a set of edges E. And then a matching is a subset M of E, for which no two edges in that subset share a vertex. We've seen an alpha approximation algorithm is an algorithm that guarantees at least to be alpha times the optimal in terms of the weight, if we want a maximum weight. We've seen a basic dominant edge algorithm, and we've shown that this is an alpha approximation algorithm. A final question to you. You see a grid graph here. 5 by 5 grid. Every vertex is connected to its neighbors to north, east, south, and west. I have a particular pattern of weights that's in this graph. And now the question to you is to carry out by hand the dominant edge algorithm. What's the weight of the resulting edge matching? And the question that is relevant to the parallelism of it, when you looked for dominant edges, how many in a particular situation could you discover at the same time in each stage?